Hi everybody, welcome back. This is Chapter 4, Lesson 10, and we're on Section 10, so that works out. We're going to be talking about balancing oxidation reduction reactions. And before we do, I have a joke for you. Oh, wait, never mind. I'm not supposed to tell you it's a joke. I'll catch you when it's a surprise. Never mind. Oh, I do have a joke though. Hold on, I have to look it up because I can't remember it. Here, this is a joke. What do you call an impatient noodle? An impasta. That's what you call an impatient noodle. Okay, so anyway, we're going to learn how to balance oxidation reduction reactions. And what you should use is what we call the half reaction method. So after you've identified whose charge is going up and who's oxidized, and whose charge is going down and who's reduced, you pull them out of the whole equation. And you write an oxidation half reaction and a reduction half reaction. When you're balancing equations, these reduction and oxidation half reactions, you must balance mass as well as charge. So I'll walk you through the steps that we use in order to do this. Okay, first we'll start with something very, very easy, and then we'll make it a little bit more complicated. So here the charges are assigned. If the charges were not assigned, you would assign the charges. You notice that tin's charge is going up, so tin is being oxidized, and this ion is being reduced. So you'll actually just pull those out of the reaction to write half reactions. We're going to write the oxidation half reaction and the reduction half reaction. So the oxidation half reaction, we have tin plus 2 going to make tin plus 4. And now we have to balance this half reaction. So there's one tin, there's one tin. But if you notice, the charges are not the same. The charge on the left is plus 2, the charge on the right is plus 4. So you go to the side with the higher charge when you're writing half reactions, and you add negative particles, which are electrons, so that the charge is brought down to equal the side on the left. So the charge over here is plus 4. If I add 2 negatives to this side, then the charge becomes plus 2. And since oxidation is the loss of electrons, they should be represented as a product. In Sn plus 2 becoming Sn plus 4, 2 electrons must be lost, and there they are. Okay? The reduction half reaction is Ce plus 4 goes to make Ce plus 3. So I go to the side with the higher charge, and I add electrons to make it equal. Now, how many electrons does Ce plus 4 need to gain to turn into Ce plus 3? Only 1. So I add 1 electron there for my reduction half reaction. Okay? Now, the electrons lost must always equal the electrons gained. And right now, 2 were lost and 1 was gained. So I have to multiply everybody's coefficient in this reaction by 2 to make sure that the electrons lost equal the electrons gained. So if I do that, then this turns into 2 electrons gained plus 2 Ce plus 4s go to make 2 Ce plus 3s. And then to get the overall balanced equation, I recombine those reactions. So my electrons, there's 2 electrons going out and 2 electrons going in, so they cancel out. So what else you have as a reactant is Sn plus 2 plus 2 Ce plus 4s goes to make Sn plus 4 plus 2 Ce plus 3s. And now what you can notice is that we're balanced with mass. 1 Sn, 1 Sn, 2 Ces, 2 Ces. But our charge is also equal because this guy has a charge of plus 2, and then there's 2 things that are each plus 4, so that's plus 8, and this side equals 10. Sn's plus 4, and then there are 2 things that are plus 3, so that's plus 6, so this side equals 10. So this equation is balanced with respect to mass and respect to charge. They will get more complicated, but these are the steps you follow. First, you write the separate half reactions. So, you write the separate half reactions. You balance everybody but H and O. You balance O using water, you balance H using the hydrogen ion, and you balance charge using electrons. If necessary, you multiply one or both half reactions by some integer so that the electrons lost equal the electrons gained. You cancel out anybody that is identical in the reactions, and then you recombine them. It doesn't make much sense until you actually try a problem. So we assign the charges and identify who's oxidized and who's reduced. Mn is, our O is -2, so that makes Mn here +7, and everybody else is okay. So Fe's charge is going up. Here's the order. You balance everyone except H and O. 1 Fe, 1 Fe. You balance O using water. You balance H using the hydrogen ion. We don't have H or O here, so that's fine. You balance charge using electrons. You add the electrons to the side with the higher charge to make the charge equal. So there's our oxidation half reaction. Our reduction half reaction is obviously a little more confusing. You take the MnO4- and it goes to make Mn +2. You balance everybody except H or O first. 1 Mn, 1 Mn. You must do the steps in this order. You balance oxygens using water. There are 4 oxygens on the left, so you will add 4 waters to the right. You balance hydrogens by adding hydrogen ions. There are 8 hydrogens on the right, so on the left I add 8 hydrogens. And now it's more complicated, but you balance charge using electrons. So if this is +8 things that are each +1, that's +8. The MnO4- ion has a charge of -1. So this side's +7. And this ion has a charge of +2. Notice, I don't count oxidation states. I count overall charges on atoms or ions. Okay? So we go to the side with the higher charge and we add the electrons to make the sides equal. This is +7, this is +2. I need 5 electrons on this side. Right now, my electrons lost do not equal my electrons gained. I have 1 loss, 5 gained. So I'm going to multiply everybody up here by 5. 5, 5, 5. And now I recombine my equations. So there are 5 electrons going out and 5 going in. I can cancel them out. And I put my reactants together. 5Fe +2 plus 8H plus MnO4- goes to make Mn +2 plus 4 waters. And you should always check yourself. That should be balanced now. So check mass first. 5 Fe's. Oh, see? I didn't write the other Fe's right up here. 5 Fe +3. 5 Fe. See, that's why you check. And I didn't even do that on purpose. 8 hydrogens, 4 times 2 gives you 8 hydrogens. 1 Mn, 1 Mn. 4 oxygens, this 4 gets distributed, there are 4 oxygens. But also check the charges. 5 things that are each +2 are +10. 8 things that are each +1 are +8. And 1 thing that's -1. So that's 18 minus 1, which gives you a charge on this side of 17. Over here, you have 1 thing that's +2 and 5 things that are +3, so that's +15. So this side is also +17, and this is your final overall balanced equation. Okay? If the reaction is taking place in an acid, or they don't tell you, you do it like I just said. If the reaction is taking place in a base, and they will tell you it is in a base, then when you get to this final step here, there's something else you have to do. So if this reaction that we just did were taking place in a base, I would have to add hydroxide ions because bases have a lot of OH minus, which will not allow H pluses to float along freely. So if it were in a base at this step, once I've recombined the equations, I would add 8 OH minuses to the left and 8 OH minuses to the right. Why 8? Because there are 8 hydrogen ions. So you would add 8 OH minuses to both sides. On the side with the hydrogen ions, they would then combine to make water. On the other side, they would exist as OH minuses. I'll show you an example of that. Balance the following equation and we'll assume it's in a base. Okay, so we'll need to assign charges. Silver's by itself at 0, oxygen's by itself at 0, silver's in a compound, it's +1. Carbon and nitrogen are not changing because you can see they're both the cyanide ions, so it's not necessary to really assign their charges. You kind of know what's happening here. You know silver's charge is going up, so you have the Ag going to make AgCN2 minus, okay? In order to balance the Cn, we have to add these Cn's over here, Cn minus, right? So balance everybody except hydrogen and oxygen first. There's 2 Cn's there. There's 2 Cn minuses there. 1 silver, 1 silver. Balance the charge using electrons. So the charge over here is -2. The charge over here is -1. So you go to the side with the higher charge, which is over here, and you add electrons to make them equal. Okay? Now, who's left? Just this oxygen with no charge. Well, it must be getting reduced. So balance oxygen using water. Add your 2 waters over here. Balance hydrogens using the hydrogen ion. 4 H pluses over here. Balance charge using electrons. This one's not bad because the only thing here that has a charge are the hydrogen ions. So we will add, let me just make a little bit of space. We will add 4 electrons to this side. Okay? 2, 4. Okay. Make sure the electrons lost equal the electrons gained. So we have to multiply everybody in this top equation by 4. So this becomes 8 Cn minuses. I'll use a different color. 8 Cn minuses, 4 Ags, 4 AgCN2s, and 4 electrons. Now put these back together. The electrons cancel out, and what you're left with here are 8 Cn minuses plus 4 Ags plus 4 H pluses plus O2 goes to make 4 AgCN2 minuses plus 2 waters. Now, normally we would be done. We check it and be done with it. But this is happening in a base. So if it's happening in a base, you add 4 OH minus ions to this side and 4 OH minus ions to this side. On the left, H plus and OH minus get together and they make something called water. So they're going to make 4 waters over here plus our oxygen. On the right, they don't get together with anything because there's no hydrogen ions floating around on the right. So you just have your 4 AgCN2 minus plus your 4 OH minuses plus your 2 waters. Now, we can consolidate the water. If there are 4 going in and 2 coming out, we can just change this to a 2 going in. It's like the net water. And that is how you balance equations in an acidic and in a basic environment. Don't panic. We'll do a lot of practice with these in class. I'll walk you through another one on Monday before I let you start heading out on your own. Make sure you do those practice problems for Monday and have a great weekend, everybody. Just one video. We'll see ya. Bye-bye.